Okay, good afternoon everyone. Welcome back to this afternoon session. Today we have Sjors Scheres, who's going to tell us about image processing and aberration correction in Cryo-EM. Thank you, Sjors.
Thank you, Giuseppe. Yes. This is the agenda for this afternoon. I thought I'd start with a intuitive introduction. Some of you may have seen these slides, so please bear with me. And then I thought that we dive a bit deeper into marginalisation and regularisation, two important aspects of Cryo-EM image processing. And then we'll follow that up with aberration correction, CTF refinements, Ewald sphere correction, and just a few mentions of some stuff that is new. So these slides are relatively old. Jan is now taller than I am. I think he approaches our director, Jan. But let's take Jan as an example protein. And we have an electron microscope, also a rather old picture. And we're going to freeze Jan in a shallow swimming pool, as explained earlier. There are many copies of Jan, and for now we're going to assume they're all in the same three-dimensional conformation. But all these copies are swimming into different orientations in this little shallow swimming pool when it is rapidly frozen in liquid ethane, as discussed earlier. Then it goes inside the electron microscope, and then in the microscope we will take transmission electron microscopy images. So the electrons will go through Jan and will generate a picture that would perhaps look much like an X-ray scan of Jan in the hospital. Okay, these are called X-ray integrals in mathematics even. So that's a very ugly picture. So I will use a black and white version to denote a two-dimensional projection image of the three-dimensional object that is Jan, which will be depicted in color. So that's the first problem that we have if we want to process the 2D images from the Cryo-EM and get an estimate of the 3D structures of Jan that we're interested in, that the data is actually recorded in 2D. Now, there's some other inconveniences, and already discussed. One of it is that we need to defocus, and also the microscope is not perfect in itself, and this introduces artifacts in the images. And these are described in Fourier space by the contrast transfer function. And if this is Jan, the 2D projection image of Jan, then simulating this with a more or less realistic CTF function, we get something like this. And you'll see that black and white has been much reduced. The overall image is much grayer. Some of the white little details have become black, and some of the white, black ones have become white. And as said, all this is described in Fourier space by a multiplication with the contrast transfer function. And I won't go into much of the detail, but it's a sign-shaped function. We'll get back to that. And as you've heard from Giuseppe this morning, at the microscope, you'll probably want to collect at various defocus, because different defoci will make the zero crossings of the sign function happen at different positions. And if we go out of focus more, then what will happen is that the first peak of the CTF will move into lower spatial frequencies, and that will generate that contrast, the ability to see the particles at low resolution more readily than in the low defocus image. But this comes at the cost of you having to deal with, in the image processing, many more and faster oscillations, and at that point, at some point, that can become a problem. So there is a bit of a trade-off there. Now, another inconvenience, perhaps the biggest one, is that Jan is rather sensitive to the electron radiation that we image him with, and we need to do that imaging under low dose conditions, which leads to large amount of noise. So this is a kind of realistic amount of noise added, and you now have to squint your eyes to see Jan in the experimental images. So going forward, I don't want you to squint too much, so I've removed the noise again. But what we'll have is 2D projection images which are convolved with the point-specs function. They're multiplied with the CTF in Fourier space, and they exist of Jan in many different orientations. hopefully all in the same 3D conformation, but we have top views, side views, etc. Now, the essence of much of the image processing that we do is something called projection matching. Let's assume we have some sort of initial guess of what Jan looks like in 3D. He might look like this, this orange little puppet. Then what we can do in the computer, we can generate two-dimensional X-ray integrals, projections of this image in many different directions, in all different directions, sampled according to some angular sampling interval. And we can make top views, side views, front views, etc. We will then compare each of the noisy experimental images of Jan. We can shift it around and rotate it around and compare it with all these different so-called reference projections and see which one fits best. And if we do that based on some cross-correlation criterion or so, then we might decide that this top view slightly from the side left is the best orientation for this particular experimental image of Jan. Now, we don't have one of these images. We have many thousands of them. And we can do this process for all these many thousands of images, and each of them will get assigned a relative orientation with respect to the orange puppet. Now, once we've done that, we can do what is called a three-dimensional reconstruction. We can take now, we get rid of the orange puppet, we take just the experimental images of Jan, they all now have a relative orientation, so we can combine all these complementary 2D views into a three-dimensional reconstruction. Now, the way that works, I think is best explained again in Fourier space. And if we have a three-dimensional object of a protein, for example, at the top left there is gamma secretase, we can, in the computer, calculate a 3D Fourier transform. So this is the same information expressed in a different space, and we can just use computer algorithms to go forward and backwards, swapping in between the two spaces. So I haven't done any calculations yet. Now, in the microscope, we might have the red dotted arrows there indicate the direction of the electrons as they go through this copy of gamma secretase, and they then give rise to this two-dimensional projection image. So this is what happens in the electron microscope. And of a 2D electron, of a 2D image, I can again use Fourier transforms and inverse Fourier transforms to go back and forth between 2D Fourier space. It's the same operation, one-dimensionally lower. So now there's something called the projection slice theorem, which says if that 2D image is the projection of that 3D object, then the bottom two-dimensional Fourier transform relates to this three-dimensional Fourier transform as a slice through its center. And the direction of the slice is perpendicular to the direction of the electrons that went through the object to make the projection image. So just this central slice through the 3D transform is the same 2D Fourier transform image as that one. Which means if I now have many thousands of 2D experimental images, I could calculate, and I know how they're all relatively oriented because I've aligned them with respect to this orange puppet. I can put many 2D slices back into the 3D transform, creating like a three-dimensional type of spider web of 2D images that all cross each other at the origin, and thereby fill up the entire 3D Fourier space. I would have to do some sort of interpolations, and then I can just do an inverse transform to get back to a 3D reconstruction. Now, that will leave us to a reconstruction which is made of only images of Jan. Okay, there are no orange puppet projections in here at all. Yet, if I make this reconstruction, it will look a little bit like Jan, hopefully, but it will probably still also look a little bit like the orange puppet. And this is the result of the relative orientational assignment that I've made are all not entirely correct because I didn't have the right 3D reference model of Jan. I've introduced errors in the angular assignments. And these errors are not harmless kind of random errors. They're actually systematic errors which reproduce the orange puppet in the 3D reference. And this is called model bias. And it's a nasty thing because I you know, this is now reconstruction just made from Jan's images, but somehow there's a bit of history of what I've done with my image processing still present in this map. And this happens to your own reconstructions too. Now, fortunately, hopefully this one is better than the original puppet of Jan, not guaranteed, but it is very often the case. Then I can repeat the process. I can make projections of this kind of Frankenstein of Jan and an orange puppet and make new angular assignments, which hopefully are slightly better, so that if I do another reconstruction, the orange puppet influence is gone. And hopefully, if I do this multiple times, I will actually converge on the true structure of Jan in 3 dimensions. Cool. Now, how do we assign that orientation to each of the images? That's then just a comparison of the projection of the orange puppet, or here a kind of fuzzy little penguin, and I have a noisy image, which is in some relative orientation, perhaps translationally or rotationally different from that image, and we're just going to calculate cross-correlation between the two images, and then I'm going to, for example, rotate this image around until it fits best, and that's the angle that I'm going to assign. I could do that for all the 3D reference projections, so you not only get the in-plane rotations, but also the out-of-plane rotations. Now, that's how the field was doing this until about 2007 or so, and in 2D 2005. And that what changed there was the concept of marginalization. And of course, the X-ray crystallographers here, especially those who've been in the field for a bit longer, remember that least squares refinements were very common in X-ray crystallography too, but they were all replaced by maximum likelihood refinements. And the difference is marginalization. So what is marginalization? We have our reference projection, and we have our noisy experimental image. I'm now going to use a statistical model of the noise, which I'm just going, as a first approximation, I could just assume that the noise in the real space pixels is all Gaussian distributed, and all these pixels are independent from each other. And given this model, I can then calculate what is the probability of observing this image given this reference in any of the orientations that are possible. And what I'm now going to do, I'm going to calculate for each experimental image, I'm going to go again through all the rotations. That kind of comparison with all the rotations of the references is still necessary. And for every orientation, I'm going to calculate this probability. And if the penguin is on its side, whereas the reference projection is upside up, then that's not very, then the images will be very different. The cross correlation will be low, and the probability of observing the image in this orientation will be, as calculated through this function, will also be low. Now, I rotate it 45 degrees, still low, but once it's in the correct orientation, then the difference between the images will be smaller, the cross correlation will be higher, the probability will be higher. So that's kind of indicated on this line is different rotations of this image, and the transparency of the image is related to the probability, which with more opaque images having higher probability. Now, an upside down penguin, if you ignore its eyes and which way its little wings flap out, is not too bad an alignment with respect to the reference. So this probability is slightly higher than perhaps some of the horizontal versions of the penguin. Now, what marginalization, this was all very similar to what we did in maximum cross-correlation, and there we just said, oh, the one with the smallest differences or the highest cross-correlation is this one. This is the angle I'm going to use. Now, marginalization does one thing different. It, rather than assigning only the best orientation, it will do a probability-weighted assignment of all the orientations. So the probability of the penguin being in the upside-up rotation is the highest, but this probability is definitely not zero, and the average penguin will be averaged over all the particles and all the orientations, probability weighted by their probability. And then it depends how much noise there is in these noisy images, whether I would still be able to distinguish an upside-up penguin from an upside-down penguin. You could imagine if you have a lot more noise than what's present on this picture, then you'd really have to squint your eyes, and you might not be able to see whether the wings are pointing up or down and whether there's actually eyes at the bottom or at the top. So in the limit of a lot of noise, all the orientations become indistinguishable, and you would be kind of smearing this penguin out rotationally. In the limit of no noise, I'm going to do exactly the same as cross-correlation, because then it's exactly clear that this is the right image. So that's marginalization. We do a probability-weighted assignment, and then we iterate through, just like I explained with the orange puppets and Jan before. So kind of an intuitive explanation why that would be a good idea. If you're not entirely sure whether it goes upside up or upside down, then hold back on making a decision that might be wrong, but you kind of just you proceed with both decisions at the same time, and then hopefully later on in the when the reference becomes bit better, then we might be able to distinguish the two possibilities. So this happens in 3D just as well, where one image of Jan will be now spread out over a whole range of orientations, because I might not really be able to, because of the noise, I might not be able to tell whether this is a view from the left or the right top, for example. Good. So that's marginalization or maximum likelihood refinements were a good step forward. You can show mathematically that in the limit of a lot of data, that is actually the best you can do. But then, of course, all data sets are not unlimited in size. And that has some consequences. That means that the experimental data alone no longer is enough to determine a unique solution to the problem. So there will be many high-resolution, noisy, probably reconstructions that are equally likely in the light of the experimental data set. And that's because this three-dimensional spider web of 2D planes that we build up at the origin is sampled a lot, because all the planes overlap at the origin. But the further you go out in resolution, the less overlap there is between these 2D planes, and so you have fewer points to sample there, and if they're all very noisy, then the signal-to-noise ratio in the average will still be relatively low, and many different averages would be equally likely in the light of those data. Okay, so that's bad news, because that means there's many structures that could be the right one. How do I now know which one is the right one? And how do I know I'm not staring at some high-resolution noisy thing that in fact is just noise and I should not interpret that, right? So the good news is you can reformulate the problem by incorporating external information. So, and that way we can formulate a new problem to which a unique solution does exist. And that in general is called regularization. And before the implementation in Rely-On, people would be doing regularization, but in ad hoc manner. So low-pass filtering, Wiener filtering were all done kind of empirically with filters, and you could become very good at this. A good image processor would know exactly which filters to tune, etc., to keep this noise that shouldn't be there at bay, but still progress as much signal as you could. This changed then with the introduction of this Bayesian framework to do the image processing. And this is Bayes' law, where the posterior is the multiplication of the likelihood function, which we were optimizing before, the probability of observing the images given the reference projections in certain orientations, multiplied by the prior, which is the probability of observing the reference. But there's no data term x here. It's independent of any data that I've measured. So, and then you divide by the probability of observing the data. Once you have your data, that's no longer relevant. So you can scrap that out, and you can just optimize a regularized likelihood function. Now, of course, the likelihood function, we could do similar assumptions and rely on. These are made in Fourier space, where we now assume the noise on each Fourier component is Gaussian and independent, and you can actually have the power of the noise varies with spatial frequency. But now the question becomes, what do I know about my cryo-EM reconstruction in advance of measuring any data? Now, the first thing that we came up with is, in terms of an explicit prior that you could optimize in a mathematical framework, is the assumption that also the signal is Gaussian, independent, and it has limited power. Now, limiting the power of the signal means that in Fourier space at higher spatial frequencies means that what I'm going to impose on real space is just some sort of smoothness. So I'm going to penalize very high spatial frequency reconstructions, only letting through good lower spatial frequency terms. Okay, now that you can all put in nice equations, which you can then actually in an iterative algorithm solve, which is convenient, and you can implement it in a program, and that was called ReLAM. Now, what ReLAM does, it estimates resolution-dependent estimates of the amount of noise you have in the images and in the signal, and it combines all of those in an optimal three-dimensional Wiener filter that filters the 3D reconstruction at each step of this iterative procedure of getting rid of the orange puppet and getting better reconstructions of Jan, but no longer with all those empirical parameters that you need to tune. So you don't need to be an expert to run ReLAM. You just put the structure in and you hit the big red button. Okay, now that's 3D refinement. You can do multiple reference at the same time, and you can do this in 2D or 3D. The algorithm doesn't change. So the same regularized likelihood function is being used to do two-dimensional class averaging, but also 3D classification to separate out distinct structures. And then the 3D auto-refinement where we keep two half sets separate so we can prevent overfitting, etc. And something called multi-body refinement. And I think Kelly tomorrow will speak a little bit more about classification and multi-body refinements, etc. What to do if the first assumption I made about Jan's data set, that there was only one three-dimensional structure, is actually not true in practice. And of course, many of our molecular machines have different conformations as part of their functioning cycle, so we're actually interested in all of those. So that's where a lot of the power of cryo-EM image processing comes from. But I won't go into those details today. So you can now do regularized likelihood optimization in ReLAM, in Thunder, in CryoSpark, etc. And also other packages use marginalization to some extent. So these use both marginalization and explicit regularization as a target. And then other packages like System and XMAP, they use maximum likelihood-based, marginalization-based classification methods. Now, one thing we haven't spoken about is how do you get the original orange puppet? And there is a problem here that the algorithm I just presented to you, this expectation maximization algorithm, is a local optimizer, and it gets stuck in local minima. And if you just start from random orientational assignments, which you could perhaps do if you don't know that Jan is an orange puppet, you could do random orientational assignments to all the particles and just hope for the best, then that tends not to work. And it was a then you get something like bad model in, bad model out, and you'll just never get rid of that orange puppet. You'll get, if you start with a blue ball rather than an orange puppet, you will not get to Jan's reconstruction. You will get stuck with something that looks like a blue ball. So, and it was Hans Almluth who introduced stochastic hill climbing as the first kind of introducing stochasticity, randomness in this optimization algorithm to get rid of, to be able to escape this local minimum that is the blue ball structure. And then stochastic gradient descent, first introduced by Ali Punjani in CryoSpark, was a big advance forward. And then we have similar algorithms now in ReLAM too. So you can just, nowadays you can start from a blue ball, which is basically calculated from random orientations of all the particles, and still get a good model out. It also helps that once you get a good structure, you can see all the main chains and the side chains, and you have a good structure. Whereas previously, when we got stuck in the blobology area with 20 angstrom reconstructions, you never could distinguish what's a good blob from a bad blob. Okay, so that was refinement. Then as an update from the last Cryo-EM course here at the LMB, there's a few new additions to image processing which I thought were worth mentioning. And the first one is in the computer, image processing to do optical aberration correction. And this is work done by Jasenko-Zivanov when he was a postdoc in the lab, mostly. So in ReLAN, you can now use CTF refinement to estimate for each individual particle what the defocus is. And the trick here is to do this against a relatively clean reference projection that you know has the same orientation as each of those particles from the projection matching algorithm. And that's different from how you would calculate defocus from entire micrographs. If you take the entire micrograph, you just take one noisy Fourier transform and look at the power spectrum, then you can see oscillations, the tone rings, as Richard already mentioned in his first talk. You can see those in the power spectrum. There's an example at the top line. But that's just power in one noisy images. Whereas if you have a very clean reference projection, which is the average of many thousands of noisy images, and you know which orientation relates your one particular particle to that reference, you can actually look at the difference between a reference and the experimental particle, and the different signal here, because you're now comparing with a very clean signal, even though your particle is very noisy, is much stronger than the one in just in the raw tomograms. So using this, you can now just step through defocus and see when does the defocus applied to the reference becomes the best description of the noisy particle. And you can do that for every particle in your data set and get per particle defocus estimates. And that's important because particles might lie at the top of the ice layer or at the bottom of the ice layer or anywhere in between. Or this is an example where actually the field of view was somehow tilted, not necessarily because the grid stage was tilted, but perhaps the whole kind of carbon foil was a bit wavy, and on one side of the micrograph images were a lot higher than on the other side. Okay, now defocus is not the only thing that matters in the contrast transfer function. There's a lot of other higher order aberrations too. So ReLAN can now do higher order optical aberration in the computer, and the first types of aberrations are so-called antisymmetrical aberrations. If the experimental image X is a projection of the volume V in some direction for that particle P, then it's being multiplied with the CTF, and this is the real value of the CTF is denoted there in CTF P, everything as a function of resolution or kind of Fourier pixel K. Then if you have a tilted beam, for example, as Richard describes, you also get phase shifts in the images. So in ReLAN, we now have a two-dimensional image that describes the phase shift for each Fourier pixel in the images, and that's this image phi k. And on top of that, those are called the anti-symmetrical aberrations. I'll come back to them in a minute. On top of that, you also have symmetrical aberrations, and these are aberrations that actually affect the real value of the CTF function itself. So the CTF function, as briefly explained by Richard, is a sine function. It has a defocus component there, dp, and it has a spherical aberration component, cs. You might have used a faceplate, as Richard spoke about. Then you'd also have a component chi that is the phase shift from the faceplate. In ReLAN, we add another term similar to actually that phase shift term from the faceplate, which is called psi here. And this is used to model symmetrical aberrations. Because, for example, if you have, examples of the asymmetric aberrations are phase shifts that are introduced by a if your beam is not perpendicular to your imaging plane. For example, if you've tilted the beam to collect data and you haven't used APHIS as Giuseppe has explained, or if there's threefold astigmatism. I'll show you an example. And then symmetrical aberrations are shifts in the argument of the sign, and examples CS itself is an example, but also fourfold astigmatism, which is something that could happen in your microscope. And the effect of that is, sorry, let me do this one first, is that the tone rings no longer are exact rings, but they become slightly, slightly rectangular or oh, what beautiful artifacts. Okay, so in Roland we use Zernike polynomials to describe these images, both phi and psi. So both the antisymmetrical and the symmetrical terms of this CTF model are described by these Zernike polynomials. And again, comparing reference projections with this model, with the noisy experimental images, now not on a per image basis, because that would be too noisy, there's not enough signal, but averaging over many images from what we call an optical group, and that might be all the images in your data set, or the images on day one until you decided to change the alignment of the microscope on day two, for example. By comparing the average signal over many images, we can actually estimate how these fields look like. And I show you one example where this was very useful in the beginning was when APHIS wasn't really commonplace yet. I think Wim Hagen had it set up in Heidelberg, but Thermo Fisher wasn't selling it yet then. But still, already we would like to shift the beam rather than move the stage, because we could collect images way faster. So if you do that, then you introduce coma. You have a tilted beam relative to the image plane if you don't look down the imaging axis, but you move the beam all the way there. You introduce a tilt in the beam, and these are then they also dance around too. These are estimated shifts, blue and red. You can see how big the phase shifts are in radians at the bottom. So the image down the center is relatively clean, but as soon as you go out of the center, then the beam tilt introduces phase shifts. And the good thing is you can model these with these Zernike polynomials and correct the images for them. One example was a 20S proteasome data set, which before doing image optical aberration correction got stuck at 3 angstroms, and then doing optical aberration correction brought you to 2.2. Why? Well, there was a lot of threefold astigmatism, so these are the antisymmetrical ones, and even some fourfold astigmatism in this microscope. That was flagged up with the people who ran that microscope. It has been the column has been realigned, and it's a lot better now. But without doing this kind of analysis, they would have not found out. They would have just said, "Oh, 3 angstroms, that's a nice structure." Okay, Ewald sphere correction. So, also mentioned by Richard on the first day. I think one useful way to think about Ewald sphere is in real space is that if you have a relatively thick object, a large virus or a big ribosome or so on, then the top of the object is at a different defocus than the bottom of the object. And now you can derive the math for that. And if you're interested, I recommend this chapter that we wrote in this book. I don't think the LMB actually subscribes to it, so just come to me for the PDF. But Takanori Nakane did a beautiful derivation of how that actually relates to what then Richard already explained on Monday, that you no longer sample the Fourier, the image on a plane in 3D Fourier space, like I just explained about with the gamma secretaries images. You now sample the Fourier components of the 3D objects on a sphere. And that means that one of the consequences is, so this no longer holds, and then one of the consequences of that is that free rule symmetry is lost. Now, that then brings limitations. If you don't account for this in your reconstruction, then you're now, if you just put out in every image as a 2D plane, whereas really the image wasn't sampled on the plane, but it was sampled on the sphere in the microscope, then you will start to limit the resolution. This is the further out in resolution you go, the bigger the difference becomes, so that at some point this becomes limiting what types of resolution you can get. And the limitations depend on the size of the particle, of course, it was about having a different defocus at the top and the bottom. So the bigger the particle, the bigger limitations there are. But also, if you drop the voltage in the microscope, the limitations become more pressing too. And that, for example, is then, of course, very relevant for the work by Richard and Chris if you want to develop 100 kV microscope. So for a 500 angstrom virus, at 300 kV, you start being limited at 2.7, but at which you could say, oh, I'm okay with a 3 angstrom reconstruction. But if you have a 100 kV microscope, then 3.6 starts to be a bit not so good, right? And even model building and model angina will start to suffer. So now, for much smaller particles, it's then, of course, less of a problem. And here, this is apoferritin, our favorite one here. At 300 kV is 1.4, which you coid say, oh, that I'm no longer too keen on, but I'll show you how you could still correct that. But at 100 kV, it becomes 1.9, which that starts to be a lot less than what you could potentially get. Now, the good news is that there are algorithms to correct for this, and Richard mentioned some, and Chris and Richard wrote this paper, which I implemented in Relan Reconstruct. So this is not part of Relan Refine. You can't do Ewald sphere correction inside this iterative loop, because sampling things on a sphere is way more expensive than in the flat planes, and it would be everything would become quite slow. But after you've done your refinement, you can do a Ewald sphere corrected reconstruction in Relan Reconstruct. This is not available from the GUI. You'd have to do this from the command line. So if you work on a very large object and or you use low voltages, then this is something you may want to have a look at when you do your structures. So then you could say, okay, sure, that's all nice. Do we actually need all this fancy stuff, or is this, what's the practical need for this? So just as an example, this was a project we did together with Abhay Kutecha, who's in Eindhoven with Thermo Fisher, and Abhay had access to this Cryos G4 with a cold fag, a new energy filter, and a Falcon 4 detector, very similar to the setup that has just been installed downstairs. And he imaged some apoferritin, everyone's favorite test sample, and then Takanori in my group processed the images and got to a 1.2 angstrom map. You've seen these images. Every non-hydrogen atom is almost an individual little blue ball of density in the map. Now, the interesting plot is at the top left here, and that's the B-factor plot, where we plot the number of particles used in a reconstruction against the 1 over the resolution squared. And the B-factor is a measure for how good your data set combined with your image processing is. So if you don't do optical aberration corrections nor Ewald sphere correction, then you have a B-factor of 73 squared angstroms. If you do the optical aberrations, you can bring that down to 38. And if you also do Ewald sphere correction, you can bring that down to 32. And that meant that combining all the 360,000 images that we had, you'd be able to reach the 1.2 angstrom resolution, which is indicated with the little black cross all the way at the top there. And then together with Garib, you could show, we showed that if you then subtract the simulated density from models that don't have hydrogen atoms, that you can even see a lot of hydrogen atoms on at this resolution, which came to a surprise to quite a few people. This one is H2O. Okay, so then you could say that's still, I can also do that without all this, because you could build a microscope, and Richard already mentioned this as well on Monday, that has a CS corrector in it. And that is true, and Holger Stark has been a proponent of this. So they published their paper back-to-back, more or less, with, it goes back-to-back with ours on a similar atomic resolution apoferritin structure, also 1.2 something, and but they did not do the optical aberration correction in the image processing, because they had a hardware corrected microscope. Now, Could I do without? Yes, but the microscope is a lot more expensive, and it also becomes a lot more difficult to work with because of how the CS corrector is set up. So you could do without it, and you could build a more difficult to use, a slower and more expensive machine. But my question would be, why would you do that if you can just do it in the computer too? So I think doing this in image processing, provided you can estimate these things reliably, and that, you know, there might be cases where that's difficult, and then there would be an argument for a microscope like this. Otherwise, I would say just keep things simple experimentally and solve some of the things in the computer. But of course, this is a philosophical discussion best had over beer, perhaps. Okay, last few things about new things in refinement. You know, what has changed in this algorithm of projection matching, and, you know, I mentioned marginalisation and regularisation. What has changed since we last did this course here in 2017? And I think the most advance has been made in regularisation. So, you know, CryoSpark and Relam, which are now used for most structures done, they both use marginalization, but the way regularization is being done is still changing. And one example is another paper from Ali Punjani. It's non-uniform refinement. And it's basically the realization that if you have a reconstruction, then, and this is a membrane protein, so it has some detergent micelle, and parts of it are floppy perhaps. So there is this realization that parts of the reconstruction are better ordered than other parts. And that just the overall regularization that Relion does, and standard CryoSpark does as well, where you just you punish signal that shouldn't be there at higher spatial frequency all equally over the entire map. They came up with a way to do a non-uniform low-pass filter, if you like, of the map at every iteration. So rather than having this one big 3D Wiener filter over the entire map, this one is spatially variant, because you can see here inside the protein region, it keeps the protein structure intact, but then here in the detergent micelle, it makes everything a lot flatter. So it's basically a low co-resolution filtered map that is being used at every iteration. And this works a lot better when there are cases like this, where there's large variations of resolution in your map. Okay, so we've been thinking a lot about this as well, and this has always kind of buggered us that, you know, oh, this kind of big question, what do I know about the reconstruction I'm going to make in the absence of any data yet? You know, I do know a lot. It's made of a protein. I often even know which protein it is, but, you know, and I don't know its structure yet, but I do know it's an amino acid chain. Perhaps it has a nucleotide chain as well. It will probably have alpha helices or beta sheets that I could predict, etc. So it seems like there is a lot of prior knowledge that I could use for regularization, but is not being used at all, because the way to make a mathematical equation that optimizes the presence of amino acid chains in a map would be complicated, right? That was the main argument for, the main reason why Relion used this smoothness prior, is because it has that beautiful formulation in Fourier space, which I can just derive all the way through. Now, it was work by Dari Kimanias here, a postdoc in the lab, together with help from Kiras Jamali, a student, that we started to look at regularization by denoising. So this is a concept from image, the wider field of image processing, where people use the output of a denoiser in an expression for the prior. And it was together with Carola Bibiane Schönlieb, who's at the maths department here in Cambridge, and Ozan Öktem at the KTH in Sweden, that we came up with a way of incorporating the denoiser into the iterative, the output of a denoiser into the iterative algorithm of Relion refinement, that you can then run these very same iterative refinements, but not only do you do this inverse Fourier transform at each step, you then pass it through a denoiser and combine it with the data in this way. So what Dari did as a proof of principle, we first worked only with simulated data. So, Dari just downloaded, I don't know, 4,000 PDB structures from atomic structures from the PDB and simulated images from them, and then trained the denoiser because he knew what each he made refinements, many refinements in Roland with the simulated data, and then we had pairs of intermediate reconstruction throughout the refinement iterations with the ground truth atomic structure from the PDB that we knew that was in there. And this denoiser does, depending on resolution, it has different effects. So here, there's a relatively low resolution noisy map. If you put it through the denoiser, you would get this image. And this would be the ground truth image at the same resolution. And a higher resolution Roland map would lead to, if it gets denoised, you kind of see it removes all the background, the solvent noise, etc., and looks more like the ground truth image. And Dari then showed that if you put this inside the iterative refinement loop, again with the same type of simulated data, then you can actually make refinement a lot better. And the top rows are just for two different structures here are standard rely on, and the middle row is this regularization by denoising, and the ground truth at the estimated resolution is at the bottom row. So you can see that the denoising works better. And that's not only a result of that final or that, that iterative application of just removing noise, because this is simulated data, we know the angles, and we can actually see that the angles get better during refinement. Now, we then worked for, I don't know, 1.5 or 2 years to try and get this working on experimental data. One problem with these type of approaches is that you're now injecting knowledge that we typically use to validate into the process. And problems like hallucination become a real problem. By definition, what comes out of these refinement will look like a protein because that's what the denoiser does. It turns something noisy into something that looks like a protein. And already in Dari's paper, Proof of Principle, we describe some of the problems here. And the implication is you cannot really trust anymore what comes out of what our kind of personal validation, we can look at the map and say, this is a crap map, and this is not a good map. And that kind of goes away if you inject too much of the denoiser information. So after a 1.5 or 2 years of work, Dari has come up with a new regularization scheme, which we call BLUSH. It's also red, but regularization by denoiser, but different, and it hides all kind of artifacts, I guess. The idea is that one problem that you see, if, for example, the particle that you want to reconstruct is very small, then noise can start to accumulate in the reconstruction, even though we do all these Wiener filters, etc. And one thing many of you will have seen is you get what we call sunshine rays. So you get all these kind of artifacts into the solvent. This is the mask used for refinements. So you can see where I haven't pulled on the data, it's nice and flat, but all these are artifacts, and they start to affect the angular assignments, and the resolution of the reconstruction gets stuck because it's a battle between good alignments from the structure and bad alignments from the sunshine rays, which starts to, at some point you start to lose. And sometimes we use much sharper masks, but here, for example, there's other things here. So what Dari has done now is a more conservative approach to denoising. He's taken a few thousand half-map pairs from the EMDB, and he's trained what's called a noise-to-noise denoiser. So where you just, from one noisy pair, you try to predict the other noisy pair, and somehow a denoiser like that learns about the structure of signal. And by doing this for many different proteins in all kind of different orientations and different windows around the boxes, he's trained the denoiser, which now removes artifacts like this, but leaves the protein structure intact. And importantly, it does not, it's relatively, also the way how it's implemented inside Roland, it keeps it all relatively conservative. So it will, we now think we have something that does not really hallucinate. We do not push it towards making it look like protein, we more focus on removing some of the artifacts that happen when things go bad. And blush regularization for this PFCRT is the same structure that I just showed slices through from the non-uniform refinement paper from Cryospark. You can now even do it even better using blush regularization in Relan. So this is just standard Relan. It would as colored per local resolution. And if you use this type of blush regularization, in a way it does something. Some aspects of it are similar as in Cryospark. It will treat different parts of the map differently. So the detergent micelle will be all one big blurry bit, as it has the denoiser has learned from all these half pairs in the EMDB, and the protein bits get maintained as protein. So we can now make this again better. And this is an example from Max Wilkinson, who was a student with Kiyoshi Nigai. He was working on this heterodimer, which is bound to DNA. The molecular weight of this complex is only 45 kilodaltons. So he'd been trying for a long time to solve this with Relan, and he always got stuck to this kind of more or less correct but relatively unsatisfying low resolution blob, which was impossible to build a model in. But using blush regularization, Dari quickly had this go to 3 angstrom. It says final, but that's not final. It's actually not polished and CTF refined yet, so we're trying to make that better. We then used Modelangelo to build the model automatically, but because that's the thing that Max loves most, we did not send the PDB model, we only sent him the map. Okay, so that will soon be available in Relan 5. So that was an overview of older things and newer things in image processing. I'll be happy to take questions you might have.